Alright guys, today we're going to work on sheet metal bend calculations. So we're going to go through the steps to make a piece of seat channel right here. Our first calculation or equation is setback, that is bend radius plus material thickness times K. K comes into our calculation as 1 if it is a 90-degree bend. Today we are at a 90-degree bend, so our K value will be 1. So we really won't even talk about it much, other than the fact that if you do a bend with a degrees of from 1 to 89, and then from 91 to 179, at that point you're going to go to the K chart and use the K calculation. Okay, so this allows us to do that. Bend allowance. We can use this bend allowance equation if, again, we're going to do a 90-degree bend. So that's what we're doing today. We're going to do this calculation. We have pi, which is also 3.14. 3.14 is also what pi, but if you've got the Texas Instrument, you should have the pi calculation or button function. Bend radius, and that is what our brake is set at, what kind of shoe we've got in our brake. Today we're working with a bend radius of 1/8, and then we're going to add that to material thickness divided by 2. Our material thickness today is 0.050. So we're running a material thickness of 0.050, divide that summation by 2, and then we come up with our bend allowance. Flats are outside dimension minus setback times the number of bends. Here today we have 2 bends, so on this flat on Bravo, we would have 2 setbacks. Alpha has 1 bend, Charlie has 1 bend, and so there we only have 1 setback. Well, let's go right here to setback. Let's go ahead and get it calculated. Setback is K of 1, so this will be the same number that we come up with here. Bend radius of 1/8. Well, 1/8, we're going to need to change this to a decimal, so we take our numerator, divide it by our denominator, and that allows us to come up with a 0.125. 0.125 is our bend radius in decimal form. 0.125 plus 0.050. We can do a little bit of quick math. That gives us a 0.175. 0.175 is our setback today. Okay, bend allowance. Bend allowance is pi. We got bend radius of 0.125. Material thickness is 0.050. Divide that by 2. Add those 2 together. Times it times 3.14, and then divide that number by 2. At that point there, we divide that number by 2. We should come up with a bend allowance of 0.2356. 0.2356. That's our bend allowance today. Now, since we're going to have that twice, we're going to go ahead and write that in over here. Setback. Setback is 0.175, so we subtract that from our outside dimension. Here in the drawing, we have a throat of 0.70. That is not our outside dimension. Our outside dimension has material thickness added to it. That gives us an outside dimension of 0.75. So we're going to subtract setback from 0.75, which is our true outside dimension. We're going to take that, and then that will allow us to solve for alpha and Charlie simultaneously. They're both the same length, they have the same dimensions, which will give us, we take 0.75, subtract 0.175, and that gives us 0.575 twice. Okay, now we have to solve for Bravo. So we have to take setback times 2, which is 0.175 times 2, and subtract that from 1.50, 1.50, and that's going to give us a flat of 1.15. 1.15. 1.15. So now we've done setback, bend allowance, we've done our flats. Our next calculation is total developed width. Total developed width is 0.575, flat A, the bend allowance, which is 0.2356, plus 1.15, plus 0.2356, plus 0.575, which would give us a total developed width of 2.771. If your numbers, when it gets down to the thousandths, if your numbers are a few off, then so be it. When it comes down to thousandths, it's very hard to translate that onto a piece of sheet metal, especially what we're doing by hand. Don't sweat that, the thousandths end of it. 2.771 will get you in the ballpark. 2.772 or 2.70 will all fall within that area. And that's going to be the total material we're going to need to fabricate this said part. So if we lay this out flat, we start with a flat sheet of metal. We've cut it to 2.771. We've laid out our bend allowances, our flats. We've done all our marks on here. To fabricate our part, we need to make one more calculation, and that is sight line, which is flats plus bend radius. So we measure from the edge, either edge, measure over, and that gives us flat plus bend radius will give us our sight line. Sight line is utilized in the brake to help us fabricate the part. And so at that point, our sight line is 0.7 is our sight line. So our sight line is 0.7. That's on this part, would allow us to be able to fabricate said part, set it in the brake, get a straight shot down, and so we can lay these measurements out, and lets us fabricate said part. The arrows here indicate these arrows right here. We lay that on top of our part so that we can remind us to slide this part in the brake. So the nose of our brake would come in, we'd clamp it down, make the bend, spin the part around, do the other side, and we'd be able to fabricate. Doesn't matter whether this is a 1-inch part in length, overall outside length, or whether we're doing a 10, 15, 20, 30 foot part. We can fabricate massive parts. When it comes down to it, we just have to make this calculation to know how wide our total developed width needs to be so we can duplicate this part and fabricate this part. You can be within thousandths regularly when you get out there, get proficient at. So setback, K is 1 unless anything outside of 90, K is 1. K is 1, and you have to use a K chart outside of 90. And the bend allowance calculation is only good at 90, and so we can almost forget about K and use these two calculations without ever having a chart if we're doing 90-degree bends. You can also use the Mechanics Handbook, 4213. They give us charts in there as well. There's times you may run across material that's not in the charts, and so that allows you to make these calculations for whatever needs it may be. Bend radius, remember when you take and go from a fraction, like 1/8, 1/16, quarter, you take the numerator divided by the denominator. It allows you to find the decimal, and that is critical. Don't forget finding the decimal. Sight line is flat plus bend radius to give us our sight line. If you have a flat with two bends on either end, you have to take setback off twice to get the correct flat measurement. That is from the outside dimension. Here we have an indication of 0.70. We had to add material thickness of 0.05, and that allowed us to come up with 0.75, which is what allowed us to come up with the correct calculations here. Like I said, guys, don't let this get ahead of you. Make sure to take lots of notes. I know I didn't write everything down. Part of it's just so it'd be clear on video. But make sure and take lots of notes. If you need to, do the calculations twice, maybe 3 times, and if you get the same thing every time, you're probably in the right ballpark. You shouldn't come up with massive numbers, depending on the part size. Flat shouldn't grow bigger than. It shouldn't be really odd numbers either, necessarily. You should see some similarities here as you begin to work. But we do get quite a bit in here, and so you guys can take this step by step and calculate parts. If we were doing an angle, and so we were just going to fabricate this part, that would change a few dimensions, but we can fabricate said part and move on from there. And so then we would only have one bend allowed, so that would change setback on Bravo, Alpha and Bravo, and we would end up with an angle. 2 bends is about as complicated as you get, and so we can do every bit of it from right there.